Hello everyone, today I wanted to share with you a very interesting problem. The problem states as following. 3-point masses M1, M2 and M3 are connected by strings of length L and rotate with an angular velocity of omega around the center of mass, maintaining the configuration of an equilateral triangle. The question is, find the tension forces of all the strings connecting the masses. This is a very interesting and challenging problem. If possible, please pause the video and try to solve the problem by yourself. I highly recommend to do so. If not, I'm here to help you. Let's go. Here I have pre-drawn a configuration described in the problem. Masses M1, M2 and M3 are located at the corner of a triangle with a side length of L. In the first picture, I have shown the tension forces on the strings with their appropriate directions. In the second picture, I have shown the vectors of the directions L12, L23, L13, indicating the direction from masses M1, M2, and M3, as well as the distances from the center of mass. Since masses are not necessarily same, the center of mass could be located anywhere within the triangle. Okay, let's dive into this problem and write some basic equations. So the first set of equations will be related to the circular motion. As you might know, the acceleration of the rotating object is given as velocity squared divided by radius, or omega squared multiplied by radius. Considering that, we can write the following equations. Minus m1 omega squared R1 equals T12 plus T13 minus M2 omega square R2 equals T21 plus T23 minus M3 omega square R3 equals T31 plus T32. This will be our first set of equations labeled as 1, 2, and 3. Please mind the negative sign in front of mass times omega squared times r. The reason is because the radiuses are directed away from the center of mass, while the centripetal force are directed towards the rotation center. So that's the reason why we put the minus sign. The directions of the tensions are indicated appropriately. T12 means the tension of the string directed from mass 1 to mass 2, and so on. Now we can write another equation relating the center of mass. M1 R1 plus M2 R2 plus M3 R3 equals to 0. This is our equation number 4. Now we can write another set of equations indicating the relation between tensions. T31 is actually same as a T13 in an opposite direction, that we put a minus sign. T32 is same as negative T23. T21 is same as negative T12. This is another set of equations that will be useful. Just by looking at the second triangle, we can write another set of equations relating the radius and the length. This will be another set of equations that we are going to use. Now we can write a set of equations relating the unit vectors of the tension and the sides of the triangle. T12 divided by the absolute value of T12 is L12 vector divided by the side of the triangle. Similarly, T13 vector divided by the absolute value of T13 is L13 vector divided by the absolute value of the L. And T23 vector divided by T23 is equals to L23 divided by the absolute value of L. So this would be another set of equations that we're going to use. As you can see, we have written 13 equations, and this is a lot. And there are some tedious process to combine all these equations and simplify our life. From the last three equations, we can get the following relations. L12 equals L divided by the absolute value of T12 multiply the vector of T12. L13 vector equals L divided by the absolute value of T13 multiplied by the vector of T13. L23 vector equals to L divided by the absolute value of T23 multiplied the vector of T23. And we can label these equations 11 prime, 12 prime, 13 prime because they are basically same as the last three equations. Just rearrange it a little bit. From equations 8, 9, and 10, we can write the following. R1 plus L13 equals R3. R1 plus L12 equals R2, R2 plus L23 equals R3. From these equations, we can get the following. L13 minus L23 minus L12 equals 0. Or similarly, L12 plus L23 equals L13. Now combining this set of equations with the equations 11 prime, 12 prime, and the 13 prime, we should be able to get the following relation. T12 vector divided by T12 plus T23 vector divided by T23 equals T13 vector divided by T13. Now using equation 4, 10, and the 13 prime, which are given as M1 R1 plus M2 R2 plus M3 R3 equal to 0, along with R3 equals R2 plus L23, and the L23 vector equating to L divided by the absolute value of T23 multiplied by the vector of T23. We can get the following relation. R3 equals minus M1 over M3 R1 minus M2 over M3 R2 equals R2 plus L over T23 multiplied by T23 vector. Rearranging this equation a little bit, we can get the following relation. M1 over M3 R1 vector minus M2 plus M3 divided by M3 R2 vector equals L over T23 multiplied by T23 vector equals L T13 vector over T13 minus T12 vector divided by T12. Here we use the fact that T23 vector divided by T23 absolute value is equal to T13 vector divided by T13 absolute value minus T12 vector divided by T12 absolute value. Now using equations 1 and 2, we get that R1 equals T12 vector plus T13 vector divided by negative M1 omega square, and R2 vector equals T23 vector minus T12 vector divided by negative M2 omega square. Now substituting these expressions in R1 and R2 of our previous equation, we get the following relation. Now we can rearrange this equation a little bit and get the following. From equation 2 that states that negative M2 omega square R2 vector equals to negative T12 vector plus T23 vector, we can get the following. Here, the last step we got from equation 9. And here we expressed the vector T23 in terms of T12 and the T13, and we are going to substitute this expression instead of the T23 in the equation above. This substitution will help us to express everything in terms of T12 vector and the T13 vector. After careful substitution, we should be able to get the following relation. You might be wondering, why did we do all these mathematical manipulations? This is the main part of the solution. I wanted to bring this equation because now I can simplify by just comparing the coefficients of the vectors. Since T12 and the T13 are independent, the coefficients multiplied to these vectors on each side of the equation should be the same. For example, the coefficient of T12 on the right side and the T12 vector on the left side should be the same. Similarly, the coefficients of T13 on the right side and the T13 on the left side should be the same. By equating these coefficients, we should be able to get our final answer. Now when we equate the coefficients of T12 from the left side and the T12 from the right side, we get the following. 1 over M3 omega square minus M2 plus M3 over M3L divided by T12 plus M2 plus M3 divided by M1 M3 omega square equates to negative L over T12. This comes when we equate the left side and the right side multiplied to T12 vector. If we take this to the other side, we should get that M1 divided by m1 m3 omega square plus m2 plus m3 divided by m1 m3 omega square equals m2 plus m3 divided by m3 minus 1 multiplied by L over T12. After this we get that m1 plus m2 plus m3 divided by m1 m3 omega square equals to m2 over m3 L over T12. Finally, we get our answer of T12 equals to m1 m2 divided by m1 plus m2 plus m3 omega square L. And this is our final answer. Similarly, when you equate the coefficients of T13 vector multiplied on the left side and the right side, we get the following. Again, after careful mathematical manipulation, T13 should be equal to m1, m3 divided by m1 plus m2 plus m3, everything multiplied by omega square L. And this is our final answer for T13. As you might already guess, the answer for T23 should be m2, m3 divided by m1 plus m2 plus m3, everything multiplied by omega square L. This is a very interesting problem, and the solution to this problem is also not trivial. So if you like this problem and if you like this solution, please let me know and subscribe to my channel. Thank you very much for your attention.